Rohit Kumar Singh. So this will be the last session. So this is an extra session, typically for 1 hour. And so in the last week, last Saturday, some of the, uh, I mean, some of the people who joined, they asked about the examination pattern and some books for problems and solutions, like to practice. And so I tried to yeah, search a little bit, and I have found out some books. So so basically, these 5 books that I could found with problems with solutions included. Here are the links to all of these books below. But not all of them would be helpful for you, because some of them are advanced level. So for example, this and this, they also have basic level problems, but also advanced level problems. This is nice. Many solved examples are there. This is also nice. So this is from an Indian author, and there are 500 plus solved problems. And this is good for preparing for exams. This one I found little advanced, so you might skip it. Uh, but uh, but it has a very detailed solution. So if you want, you can also take a look at this book. So these links will not. I mean, some of the links will give you free PDF, but not all of them. So you guys should download it from some, like libgen or somewhere. I don't know. I don't recommend to buy them. So you can just download it from a free source from internet somewhere. Okay, and beside these, there are other books also that you can search and find. If you find it suitable, you can go through them. Okay, anyone has any question here? Okay, and regarding the exam pattern, so what I could what I could find, it's a computer based exam, and mostly it will be MCQs. Okay, and if you guys have registered for the exam, you must have received some bulletin about it, right? I'm not sure if you have received or not, but I could find this document, which I'll just share in the chat. So you can open it. Uh, this is about the time. This is about here you can find all the guidelines for the exams. So this is from the official NPTEL website, and I could not find the exact exam pattern instruction mentioned anywhere. But if you have registered, you must have received an email regarding the all the information about the exam. So please go and check. Has anyone received it? Can you confirm? Has anyone registered for the exam? Hello? No one? Okay. Swastik has registered. So have you received any information about the examination pattern?
No, sir, we haven't.
You have?
No, sir.
Oh,
No.
no, you have not. Okay, okay.
Sir, in the email it was mentioned only we will have pen and paper mode examination.
Oh,
That's only, sir.
it's a pen and paper based.
Yes, sir.
Okay. So yeah, I'm not sure. Because I could not find it on the official website. So there is only it's only written that it will be computer based exam. So, but you are saying it will be pen and paper based. So I don't know if it. I think it varies for different courses. So I would say uh, just email to NPTL, so you can contact the NPTL about it, okay, and just confirm with them what will the pattern of the exam is, okay. That's what I'll suggest, and then you can prepare accordingly for it. So yeah, and also there is a discussion forum, right, for this course. You can also ask there. uh, I don't know if anyone will respond to that, but you can try. But yeah, NPTL guys will respond, or the Swayam portal guys. You can write an email to them. The email should, I mean, the contact email should be available on the website of NPTL. So yeah, because I'm not, I mean, I don't have any information about the exam. It is conducted by Swayam portal, so yeah, you can check with them. But yeah, these books can help you for practicing. So there are problems, so I'll suggest go through the problems and just try by yourself once, and then if you don't, if you are not able to solve it, then you can look at the solution, and then you can check what you have done wrong, and like that. Okay, so yeah, so for the rest of today, I would like to discuss something. So last week, I mean, in the last session, we had this problem from the Bose-Einstein condensation topic, where it was given that the critical temperature for the Bose-Einstein condensation depends on the number density as n to the power 3 by 7, okay. And also it was given that the density of states is equal to a to the power a epsilon to the power sigma. So epsilon it is the energy of the states, okay, and it has a sigma dependence. So and we know that so what from the derivation of Bose-Einstein condensation that we saw, we had the dependence on energy states as square root, right? And there we got the dependence of critical temperature on n as 2 by 3, right? Yeah. So so I mean, the question asks what is in general what could be the case if you have a sigma dependence. So here sigma is half, right? So if you have a uh, in general, if you have sigma dependence on the energy states of the density of state, what will be the relation with this critical temperature, okay. uh, so this, I mean, it would be something like this. So some n to the power some function of sigma, some function of sigma, and we need to find this sigma, I mean this function of sigma. And so to do this, we have to go through the integral once again. So so this total number of particles is given by this integral. So this is n by v basically. Volume can be divided in on the left hand side. Right, this everyone knows, right? We discussed it many times. So this is and this integral we have to do. And if the energy density is given like this, then we can just substitute it. So n by v, we can write it small n, which is the number density, and we can take a outside, and then you have epsilon to the power sigma, and the denominator is same. Okay. Okay, now this integration we have to do as a function of sigma. Okay, and but what we are concerned with is the uh, temperature dependence, right? Because that will give us the relation between the temperature T and this N. So somehow we need to take this temperature term outside the integral, because anyway this is a constant for this integral, right? So uh, how to do that now? First of all, uh, we know that this should be discussed in the lectures. So when the temperature reaches the critical temperature, okay, the chemical potential goes zero. Okay, this everyone knows. So intuitively, to understand this, when you reach the critical temperature, you get the Bose-Einstein condensate, right? And the Bose-Einstein condensate state is such that you can add so chemical potential getting to zero means you can add or remove one particle, you without without any effort, so you don't have to spend any energy to remove or add one particle. Okay, so chemical potential is intuitively just the energy required to remove or add one particle to the system, right? Yeah, anyone has any doubt? Siddheswar has raised his hand. Yeah, go ahead. Do you ask something? Do you want to ask something? Okay, maybe it's by mistake. So yeah, so I'm saying that chemical potential means reaching zero means uh, ba- little to no energy required to add or subtract one particle in the system. So with this condition, this integral becomes, so I'm putting mu equal to 0, so this is just epsilon by kt and minus 1. Okay, now what you can do is we can substitute uh, epsilon over kt as x, okay, which will give you epsilon equal to x kt, and d epsilon equal to kt dx, right? And so we can take the and also this T is now critical temperature, so Tc. And now we can take this temperature outside because it is constant. Uh, the integral is on epsilon only. So finally you will get Kt, and since epsilon has sigma here, so it will be sigma and 1 Kt from this dE, so sigma plus 1, right? And the limit won't change because at 0 you get 0 and at infinity you get infinity, so the limit will be same, and you will have x to the power sigma ex minus 1 dx. Okay, so everyone is fine with this till here? Anyone has any doubt? You can ask. So I've done a simple substitution to take this temperature outside of the integral. Okay, so finally we get this. So you can just say that okay, the N and critical temperature is related by this. But we still have this integral, right? And here also the temperature is there, so the critical temperature is still there, right, in the e to the power x dependence. But the the beautiful thing is when you do this integral, okay, from 0 to infinity, you don't the result that you get, okay, does not depend on the critical temperature. So this integral is a very special integral, okay. You cannot integrate it using any conventional methods. And so this integral, uh, I'll just write it. So it has, so integrating it, you will get gamma function of sigma plus 1 and zeta function of sigma plus 1. Okay, so this is what you get from this integral evaluating it. You cannot evaluate it by hand. So this is a standard integral form. Okay, and you notice this, there is no temperature dependence in this term here, right? This is just a function of sigma, and the temperature dependence on sigma is just only in this term. Okay, so you have this dependence here, right? And if if you take the power on the other side, the critical temperature depends on number density as 1 over sigma plus 1. This is what we wanted, right? This is what we wanted. So we got our sigma dependence, which is 1 over sigma plus 1. Now if if you have any general density of states given, so suppose we were given you know 1 by 2, you can just put here sigma equal to half, and you can get so 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 for 1 by 2 what we had, let's see if you get this. So we will put half plus 1, and this is basically 2 by 3, which we had for the 3 for the case for the ideal Bose gas, right? And so if you in general, if any density of states is given, you can find the critical temperature dependence on the number density. Okay, so this is what was left on the last day. I promised that I will try to work it out. So these these relations you have to remember this. So there will be short questions in the exams that can be solved using these simple relations easily. Anyone has any questions? Okay, if not, then we can go to another problem. So from last 2 weeks we are discussing Bose gas and Bose-Einstein condensation, and we also discussed the Fermi statistics, and the Fermi energy concept of Fermi energy and all, and but we did not have much problems on it. So I thought I would just do a problem on it, and so that you guys will, so it will be a revision of this concept. So basically, question. So let's read the question first. So if the number density of a free electron gas in 3 dimension is increased 8 times, its Fermi temperature will. These are the options. Okay. So whenever you get this Fermi temperature, Fermi energy, or Fermi momentum, then you have to consider the case when temperature goes to 0, right? There, so what happens there? There, the occupancy, mean occupancy of a Fermi gas, which is given by this here, +1, -1 is for Bose gas. Okay, this will become either 1, okay, if the energy of the states is less than mu, or it will be 0 if energy of the states is greater than mu, right? So you get this kind of step function. So at mu, we call it mu naught, okay? So it is 1 if it is if the energy of the states is less than uh, mu naught, or greater than 0 if it is greater than mu naught, okay? So basically at t equal to 0, your mu is mu naught, right? And this mu naught is basically called the Fermi energy, okay? Epsilon of f. And so what happens is all the single particle states up to e equal to mu naught are completely filled with one particle each, and those states which are with epsilon greater than mu naught are empty, right? So only those energy states which are up to like epsilon equal to mu naught, these are completely filled, okay? So this is so this is very different from the Bose-Einstein condensation. So why we don't have Fermi condensation? Because of this Pauli's exclusion principle, because no two particles can acquire the same energy states. So that's why we don't get a condensation. We don't get all the particles in a single energy state. Instead what we get is there will be a threshold of energy which is mu naught, up to which all the energy states are completely filled with one particle each, okay? And above that energy of the state, which is Fermi energy, ef epsilon f, all the states will be empty, okay? So this was the concept of Fermi energy. And then you can have all kind of definition about Fermi temperature, Fermi momenta and all. So let's remind you how to get that. So first we can calculate the total number of particles, which will be just integration of the density of states from 0 to ef, right? This will be the total number of particles, because we know each state has one particle. So we have to just count the number of states, and which is just this integral, right? And we know the density of state is given. So density of state is given by this formula. I hope you remember, guys, right? So this just the volume on phase space, which is the v 4 pi p square dp. This is the volume in phase space divided by the h cube, which is the smallest volume possible in the phase space. So this is the total number of states, and there will be a g, which is the degeneracy factor if the states are degenerate. And yeah, so then you can just we can just do this integral, and but we can write it, sorry, square dp upon de, and you can just plug it here in this integral and do the integration, and you will get 4 pi gv. So this p square will be p cube by 3, and the integration will be now from 0 to pf, which is the Fermi momentum. Okay, so you will get the pf cube, and this Fermi momentum is related to Fermi energy by this formula, this classical formula. Okay, and you can get back the uh, so you can rearrange this one, so you can take the v on the left hand side, 3h cube, and so we can rewrite it in terms of Fermi energy. So Fermi momentum in terms of Fermi energy will be just 2m ef to the power half, right? And here it is cubed, so it will be 2m ef to the power 3 by 2, right? So basically from here you get this relation, so it is 2 by 3. Okay, the Fermi energy depends on the number density by 2 by 3, and this is what we wanted to have, right? Because the question asks, if the number density is increased 8 times, what will happen to the Fermi temperature? Oh, but we still not have gone to Fermi temperature, but it is very easy, right? We know that Fermi energy depends on Fermi temperature by this relation, right? There can be some factor here, so we know that for ideal gas it is 3 by 2. For Fermi gas this factor might change, but the dependence on temperature will be simply a linear relation, right? So basically Fermi temperature will also depend on the number density by 2 by 3. Okay, so if you increase the number density by 8 times, what will happen? So Tf1 over Tf2 n, and it is 8 times n, 2 by 3. So we have to find this ratio. Actually it should be other way around, but it's fine, let's do this. So it will be 1 over 8, so 1 over 8 we can write to the power cube, 2 by cube. Okay, so basically it will be, you get 1 over cube, and 1 over cube get cancelled, so you get just 4. So it will be 4 times. So Tf2 will be 4 times of Tf1. Okay, so the Fermi temperature will be increased by 4 times, by a factor of 4. So this is also a nice thing. So these formulas are very helpful. You guys should just take a note and remember these. This will help in solving the problems. You can also derive it if you remember this formula for density of state. You can derive everything. Okay, these are simple relations. Okay, so yeah, this was the problem that I wanted to discuss about Fermi energy. Anyone has any doubt or any question? Please ask. I mean, if you can ask anything. If you don't know how this density of states formula is written, you can ask. I can try to explain. You can ask anything that you if you have any doubt. Is it fine with everyone? I don't see any. Okay, it is fine. Okay, so yeah, this was the last problem. Uh, and regarding the exam pattern, you guys should confirm. Okay, you should mail them and ask what will be the exact exam pattern, and um, I can write to them. Maybe I can write to them so that you can so that they can send you an email with all the information. I will also do that. Okay, so you will receive an email from NPTEL team regarding the examination pattern. I will just tell them to write you guys an email. Those who have registered for the exam. Okay, and so I already told you about these books, and you can go through them. There are problems and solutions in these books that you can work out. Okay, so this slide will be available on the NPTEL portal. You can download it and go through these links to find the name of the book and all. Okay, so that is all for today. So all the best for the examinations. I hope I was able to help you in this course. Okay, so thank you guys. Thank you for joining.
Thank you, sir. Thank you, sir.
Thank you. So bye. See you.